Good evening, Sal Z. Our next speaker, Ben, is a math aficionado working undercover as a security researcher. He dabbles in reverse engineering, cryptography, and machine learning, though his secret dream, well, it's not so much of a secret now, is finding an application of metric space theory to anything at all. Put your hands together for Ben.
All right, hello everyone, and welcome to Rust binary analysis feature by feature. Well, I was already introduced, but here I am introducing myself again. My name is Ben. I am a security researcher. My day job involves a lot of reverse engineering, but also sometimes machine learning and cryptography. Now, do excuse me, I'm a bit under the weather today, so if and when I collapse in a fit of coughs, have some patience, please. So, Rust is great, it's fast, it runs close to the metal, it prevents whole categories of memory safety bugs, but unfortunately reverse engineering Rust binaries has a pretty notorious reputation. So in order to alleviate this sad state of affairs, this talk is going to have three main goals. First of all, we're going to understand a Rust binary beginning to end by getting to know all of the ways that the features express themselves in assembly. Related to that, we're going to get more familiar with the way that the Rust compiler expresses itself and expresses language features in assembly language. And finally, hopefully, we're going to reach a state of better and greater understanding of how the Rust compiler thinks and operates. Now, this talk is not the equivalent of reading the book Practical Malware Analysis, but for Rust instead of C. Right? Understanding a Rust binary is not the equivalent of being able to understand every Rust binary. You're not going to walk out of here ready to face the big, bad, evil jungle of malicious Rust binaries out there. Everything here is compiled in debug mode with the symbols intact. This is meant to be more like a friendly introduction to the way that the Rust compiler thinks in a calm and controlled environment. Now, this talk is based on a gigantic blog post. We only have 30 minutes, so you're going to get just the highlights, the most exciting parts. There's also an accompanying Git repo where all of the sources and all of the binaries that you're going to see are available for you to play around with to your heart's content. So let's start with some basic programming language features and how the Rust compiler expresses them in assembly language. In order to test that out, we put together a sample program. There's like nothing special here. A bunch of person objects are being constructed, and each person has a name, an age, and a favorite beetle. And then their ages in the future are being printed out, and someone's favorite song is being printed out too. The specifics don't really matter. I just wanted you to have the general context of where all of the source snippets that you're going to see later are coming from. Now, when reverse engineering a Rust binary, probably one of the first things that you're going to run across is this, right? Rust binary hard-coded strings do not have null terminators, which means that usually if you're opening such a binary in IDA, for example, it's going to squish together all of the strings into like one mess. So one way to fix this in IDA, for example, is to go to the beginning of the string, press asterisk, and then manually feed in the correct string length. But another thing that you could do is, well, 3 weeks after we published the original blog post that I talked about earlier, Hexrays published their own Rust analysis plugin tech preview, which is aimed at solving exactly this issue. So I encourage you to try this out too. Now, when doing reverse engineering, it's always very useful to look at the state of dynamic memory while the program is executing. You're going to see a lot of things that you don't see just looking at the static assembly. And in this case, one of the first things that jumps at you is how the string object is constructed under the hood. It's nothing very complicated. There are 3 fields: len, keeping track of the string length; buff, keeping track of a pointer to the raw contents of the string; and capacity, which is keeping track of the string's current maximum capacity. Like I said, nothing too complicated. But first of all, it's useful to know. And second of all, it's going to pop back up in the right moment when you talk about sum types. So it's useful for you to keep this in mind. Now, the final basic feature I wanted to talk about is this for loop, which looks pretty innocent on the surface, but like under the hood, it's an alien wearing human skin. It's very complicated for a for loop. There's like an object being constructed here, and some function is being called on it repeatedly. Very strange. So let's dive in and see what's going on here. Well, yes, an object is being constructed here, something called a range object. It has 2 fields, a start field and an end field. Start is initialized to 0, and end is initialized to 10 in this case. And the function is being repeatedly called on this object. This function is called next. Now, the next function is doing two things. First of all, it returns an object. And this object is of a type that, for the time being, I'm going to call a maybe integer. Maybe it's an integer, and maybe it's nothing. This is implemented using two fields. The maybe field, which is 0 for nothing, and 1 for there's something here. And an integer field for keeping track of the actual integer. Now, the logic according to which the next function decides what kind of maybe integer to return is as follows. Try following this. If the start field is less than the end field, then the next is going to return the value of the start field as a maybe integer with the maybe field set to 1, like an actual integer is there. But if the start field equals the end field, or God forbid, it's larger than the end field somehow, then the next function is going to return a maybe integer with a maybe field set to 0, which means it's just returned nothing. Now, after deciding what maybe integer to return, the next function does another thing, which is mutate the range object by incrementing the start field by 1. So if you follow this, what is now going to happen when we take the range object and repeatedly call next on it? First, next is going to return a maybe integer, like an actual something, with the integer set to 0. Then it's going to mutate the range object. The start field is now 1. Next is now called again, so now you're going to get the integer 1 returned to you as something, an actual something with a maybe field set to 1. And in that way, you're going to get 2 as a maybe integer, 3 as a maybe integer, and so forth and so on until we reach 9. Now, after we get 9 as a maybe integer, the next state of the range object that next is going to be called on has start equaling end equaling 10. Now, based on what I've explained earlier, when next is being called on this object, it's going to return nothing, a maybe integer with the maybe field set to 0. I hope that looking from the outside in, you are able to appreciate that this entire contraption is emulating the exact logic needed in order to implement a for loop. You're getting all of those integers, one after the other, 0, then 1, then 2, etc., etc. And then finally, when there's nothing more to iterate on, this function next is going to return nothing. This signifies that, like, the loop is done. Now, I will excuse you for looking at this thing and calling it over-engineered, but actually this is a pretty useful construction because it allows the Rust compiler to perform iteration or for loop logic on structs and objects that are more complicated than just integers, and we are going to see an example of this later. Now let's talk about the type system in Rust, and more specifically, let's talk about sum types, because we need to understand sum types in order to understand error handling in Rust. And we need to understand error handling in Rust, it turns out, in order to understand even the most basic stuff that happens in a Rust program once it is compiled. So what is a sum type anyway? Well, it's kind of like an enum, except each variant of an enum of this enum can potentially wrap another data type. I think the easiest way to understand it is to see the example, such as the example on the screen right now. This sum type 1 has two possible variants, a 1 option wrapping an integer and another option which also happens to wrap an integer. Now, how does the compiler implement this thing? Not in a complicated way. It allocates two fields, two keywords. One is the variant field, which keeps track whether this is a 1 option or another option. One option is encoded as 0 and another option as 1. And another field which keeps track of the value of the integer being wrapped here. This is again not complicated. If I had given you the task to implement this thing, you would have implemented this in the exact same way. Unfortunately, the way that the Rust compiler constructs sum types at the assembly level is not always so straightforward. When we tried to compile something a little bit more complicated than that, which is like almost the exact same sum type, but this time the another option variant was wrapping a string, we ran into something strange. You would naively expect this to take up 4 fields, right? Because the string takes up 3, we saw that earlier, and you will need another field in order to keep track of the variant, so that's 4 fields in total. But instead, the compiler gets clever. It says, I'm not going to do it in 4 fields, I can do it in 3. How does it do that? It notices that in a string object, the buff pointer is not legally allowed to take the value 0. Right? Rust doesn't have the amazing feature known as a null pointer. So based on this, the compiler decides to assign the possible value of buff as 0 to the possibility that this is not a string at all. This is an integer, and it's the one option variant. And when the compiler needs to generate code that's going to check what variant this is, it's going to generate code that goes straight to the buff pointer and compares it to 0. If it's 0, we're looking at the one option, otherwise we're looking at another option. Pretty simple, after all. So now we're ready to talk about error handling in Rust, and specifically the types option and result. Congratulations, you already understand option and result. These are just regular sum types. It just so happens that they come with a ton of syntactic sugar out of the box from the Rust language, but otherwise at their heart, they're just sum types, right? You could have this, for example, sum type 6, which has two variants, one option wrapping nothing, and another option wrapping an integer. Completely analogously, by just renaming the variants, you could have a sum type called an option of an I64, where the variant none is wrapping nothing, and the variant sum is wrapping an integer. Kind of like something that can be an integer or nothing. That's right, that's the maybe integer we saw earlier. That's like its proper name. It's an option of an I64. Similarly, just like you could have a sum type 7 there on the bottom left, which has two variants, one option wrapping an integer and another option wrapping a string, you could rename the variants and end up with this type called the result of an I64 in the string, where the variants are an OK variant, which is wrapping an integer, and an error variant, which is wrapping a string. Just as a hypothetical example of when you would want to return a type like that, for example, you have like a function which is performing some arithmetic. If everything went fine, you will be returning the OK variant, wrapping the result. And if something went wrong, you will be returning the error variant with like a description of what went wrong exactly. So how do these option and result types look like in assembly after the compiler is implementing them? Well, there's no huge surprise here. We already saw how the compiler implements sum types. So like I said, these are just regular sum types. If the compiler can piggyback off of some kind of impossible value, such as the buff pointer in a string that cannot take the value 0, then the compiler is going to do so. And if it cannot, it is obviously not going to do so. The one new thing in this slide that you did not see earlier is the way the compiler implements the option of a beetle. Now, a beetle is an enum that goes up to 3, 0, 1, 2, or 3. And the compiler, again, piggybacks off of an impossible value, this time the impossible value 4. The compiler assigns 4 to mean none, like there is no beetle there. And in this way, the compiler is able to implement the option of a beetle in just one field instead of two. So we're ready to talk about something called the try operator. Now, a lot of functions in Rust return options and results. And if you're going to try and handle each one of those returns option and results with boilerplate code, checking if this is like you got the result which is fine or not fine, then your program is going to end up pretty clunky. It gets very unwieldy. So for this reason, Rust introduced like this little toy called the try operator, which is kind of a shorthand. You put it next to an option or a result or some other type which can be like fine or not fine. I'm going to say it has like fallible nature, and later I'll say more precisely what I mean by that. And from the programmer's point of view, what this question mark does is that when put next to like type that can be fine or not fine, it checks if the type is fine or not fine. If it is fine, the value inside gets unwrapped, meaning if you earlier had an like OK of an integer, now you have an actual integer and the function can continue its computation. But if the variant is not fine, then the logic gets short-circuited and this error value gets propagated back up the stack immediately. This error value becomes essentially the function's return value. This is like a very handy and idiomatic way to handle errors, options, and results in Rust. So there's this shorthand for it. And the way that it gets implemented under the hood by the compiler is that for each such type that has like fallible nature, it can be fine or not fine, there's a function called branch. It's not the same function for all the types. It's a different function per type. And later we're going to talk about how and why exactly this is true. But the point is that after branch is called on such a type, it returns another sum type called the control flow. The variants of a control flow are pretty self-explanatory. Continue means everything's fine, execution can continue, and break means stop, something went wrong, propagate the error value back up the stack. So now we're ready to talk about the final sum type that we're going to see today, which is the control flow of a person and an error. Why do we care about that? Because in the original program, a bunch of these person objects are being constructed. and the construction can fail. So the programmer naturally puts a question mark, like the try operator, next to the result value that results. And now the compiler, in order to decide how to continue, in order to generate code that's going to decide how execution is going to proceed, it's going to check what variant is the control flow struct that was generated by calling the branch function on this result. So in order to understand how this check is going to look at the byte level, we need to understand how this control flow structure is structured at the byte level. And, well, we already know how a person is structured, right? They have a name, which is a string, an age, which is an integer, and an option of a beetle, which goes up to 4. Remember, 4 is none. And there's, of course, the error enum, which is just a regular enum. Now, it's not a huge mystery how the compiler is going to handle finding space for the error enum. Once the person structure is not there, there's plenty of space left. The error enum can go instead of some part of the name or the age or whatever. The interesting part is how the compiler is going to encode whether this control flow variant is a continue variant or a break variant, meaning if something went wrong or not. And as it turns out, it piggybacks off of the option of a beetle enum again. Right now, it notices that the value 5 is impossible, so it assigns the value 5 in that field to mean that this control flow structure is a break variant, and effectively something went wrong. Now, all of what I've just told you jointly implies is that if you take a very simple idiomatic program that constructs a bunch of these person objects and then uses the try operator on each because the construction can fail, in order to see if construction went well or not, the compiler is going to look at that person and compare their favorite beetle field value to 5, where I'll remind you, according to the programmer who programmed this, the enum values only go up to 3. There are supposed to be only 4 beetles. So when we first saw this, we got really, really confused. We thought that we understood something fundamentally wrong. But based on everything that I've just told you, it should make complete sense to you why, after a person object is being constructed, the compiler is going to check if the construction went well or not by approaching this person and asking them whether they really happen to like beetle number 6 out of 4. Right? Maybe you originally thought there were only 4 beetles, but you were mistaken. There are 6. John, Paul, George, Ringo, none, and an error has occurred during the construction of this person object. So now, with this new insight in mind, we're ready to talk about the trait system in Rust, more specifically traits, generics, and monomorphization, and the surprising second-order effects that these have for the way Rust binaries are constructed and are best approached. A trait is kind of like a Java interface, but better. This is really not a place for me to delve into that. The bottom line is that it's kind of like a contract that the type can implement. For example, if you want your type to implement the person trait as it shows up on screen here, your type needs to implement the functions name, age in future, and favorite beetle, all with these specific exact signatures. Now, Rust has a nice feature called generics, also available in some other programming languages. And in Rust, among other things, something you can do with generics is implement a function, instead of for some specific concrete type, implement a function for every type in theory that implements some specific trait, such as, for example, on screen, you can see an implementation of a function foo for every type T which implements the person trait. Now, of course, when the compiler is putting together the binary, it's not going to be able to call some abstract notion of a method that it should exist in theory because the type T implements the trait. What it's going to do in practice is that it's going to use basically the image on the left, the implementation of foo, as kind of like a skeleton or a mold. And wherever there is a call to a method that should theoretically exist, the compiler is going to consider that like a hole. It's going to patch that hole by inserting a call to the actual implementation of that concrete type for that method, which is guaranteed to exist by the compiler because we require the trait bound. This implementing a function like this for any type that implements a specific trait is called the blanket implementation. Now, an immediate consequence of the existence of blanket implementations is that you can end up with like 7 or 8 or however many different copies of the same function just implemented for different types. And nothing here is happening at runtime regarding the understanding of what type is being handled. There's no dynamic dispatch here. So this process of creating different functions that are almost the same, just the call addresses are different here and there, is called monomorphization. So how does this whole ecosystem of generics, traits, and monomorphization affect the structure of Rust binaries? It turns out in many interesting and alarming ways. First of all, this is more of a general note. It's really very useful to be thinking in traits when you're looking at a Rust binary. Like everything I've talked about up to now was actually based on traits, even though I kind of skirted around that fact. You can only call println on a string because it implements the display trait. You can only call next on a range object because it implements the iterator trait. You can only call the try operator on an option of a beetle because, remember earlier I said it has like fallible nature. It can be fine or not fine. The practical meaning of this is that it implements the try trait. And tying into that, if you walk into a Rust binary and try to understand what functions you're looking at without thinking in traits, you're going to have a really bad time, and especially if you have access to the symbols. The auto-generated symbols by the Rust compiler are not so great, not so legible. They become a big mess pretty quickly. There are all sorts of factors at blame for this. I think generics is the biggest one. But the thing is, there's hope. Because if you look at the top example here, for example, a sane programmer would call this function just by the name next, which actually appears somewhere in there. I put an error there to point you at it. And similarly, you can understand a lot of what these functions do and what they are for if you are thinking in traits and you are laser focused on 4 questions, which is, this is an implementation of what function, for what type, returning what type, and all of this is possible because of what trait. So for example, if you look at the completely illegible example on the bottom, if you go hunting for these needles in this jumble of a name and in the context surrounding the function call, guided by the 4 questions I just outlined, you will be able to find out that this is an implementation of the function next for a values type, returning an option of a person, and all of this is possible because the values type implements the iterator trait. Another implication of the whole traits ecosystem immediately follows from the way monomorphization works. It concerns your favorite function similarity engine. Because of monomorphization, like I said, you can easily get many copies of a function which look almost exactly the same. Just some call addresses are different, and if you're dealing with library code, these can also be spread across many different binaries. So of course, your favorite function similarity engine can get confused by this. If it's looking at a blanket implementation and saying, hey, I recognize this looks like function X for type Y, maybe you want to give the function X part more credibility than the type Y part. Now, this only happens for blanket implementations. If you're looking at different other kinds of implementations, such as an implementation of a function or a trait for a certain concrete type, or somewhere where the programmer asks the compiler to derive an implementation using what's called the derive macro, then you're not going to get this phenomenon. The final implication that I wanted to go over of this whole trait ecosystem is what I would like to call the issue of modularity. In the same world, user code calls library code. But in Rust world, you can easily end in a situation where the converse is true. How so? Suppose Eve is writing some kind of program which is sorting people's birth records. And she calls the sort function on the array of birth records, but then the compiler, the Rust compiler, like it likes to do, it complains. It says that the record object does not implement the order trait. The function for atomic comparison of 2 records is missing, the CMP comparison function. So Eve implements this function, and then the program compiles, and she is happy. Now, 3 months later, we are looking at this program, and we are essentially looking at a situation where the function sort, which is library code, if didn't write it, is calling a function, which is calling a function, which is calling a function, which 12 levels down is eventually calling the one piece of user-defined code that we actually care about, this comparison function that Eve wrote. So this is a spicy situation, and you need to be ready for it. Like the adage goes, now you know, and knowing is half the battle. Now, the final implication of the trait ecosystem and of thinking in traits in general that I want to go over is the existence of containers and code that manipulates containers. Rust has several built-in containers. The two most important ones are hashmap and vector. Hashmap is kind of like a Python dictionary. If you look, for example, at this source, what it's doing is that it pulls these person objects out of a vector, then takes their names and ages and pushes them as key value pairs into a hash map. And if you go into this assembly without thinking in traits, then you're going to have a really horrible time. But if you go in with a disciplined mind and focus on the 4 questions that I outlined earlier, it turns out that what's going on here is not so incomprehensible. You start out with this vector of person objects. Now, this vector implements the into-iterator trait, so the compiler can call into-iter on it. The result of this call is an into-iter object, which in turn implements the iterator trait, so the compiler can repeatedly call next on it. Remember, this is for loop logic. It's going to, every call to next is going to return an option of a person, either something, a person, or nothing. So as long as the compiler keeps getting these person objects and not nothing, which signifies that the iteration is done, it's going to call name and age in future on these person objects, which is possible because the person object implements the person trait. Now the compiler has the person's name and age, almost, because age in future can fail. So actually it returns a result. The programmer is going to put the try operator there. Under the hood, the compiler is going to call branch, which is possible because this result implements the try trait. We've been over this already. And finally, the compiler now actually has the person's name and age, and it can call the insert function on the hash map with this name and age as parameters. The insert function is implemented for this kind of hash map directly and not as part of any trait. See, not so terrible after all. Now, the final subject that I wanted to touch upon, I don't know how much time we have left, but it's not huge, it's like 3 or 4 slides, is the subject of iterators and closures. Now, an iterator is something you can call next on. We've been over this already. And a closure as well, it's kind of like an anonymous function, very convenient to use as an argument or a return type of another function. Closures have many other interesting features and properties. This is not the place for me to delve into that. The bottom line, as far as we are concerned right now, is that together, iterators and closures allow you to write code like what you see right now in the bottom image of this slide, which is the most beautiful code in the world that no one except for you is going to be able to understand. Now, unfortunately, some people swear by this coding style, or so I have heard, so we felt compelled to push this through to the compiler too and see what comes out the other end. And we started out with a simple iterator expression, and we got immediate weirdness back out. Now, on the surface level, there's a sum function being called here, which should make sense, right, after the range object is being initialized. The sum function, which is part of the iterator trait, is delegated to the sum function, which is part of the sum trait, all right. This, in turn, gets delegated to the fold function, which is back again part of the iterator trait. Now, the way that fold works, fold is something called an iterator consumer. It has access to a certain closure. And what it does, it takes the first 2 items of the iterator, gives them as arguments to the closure, and gets a result. Now it takes this result and the next item of the iterator, gives them as arguments to the same closure back again, and gets a result again. Now the result and the next item of the iterator again and again and again until the iterator is finally consumed. I hope you can see that in the special case where the closure in question is simple addition, then this fold operation implements summation of this iterator items. So this is how summation is implemented under the hood, under this like lasagna of calls, concluding in closure. And now we're ready to see the next iterator. Now, before I go to the next iterator, I just wanted to point your attention to something interesting, which is that the addition closure here, contrary to what you might have expected, it's not given as an argument to the fold function. The call is spliced directly at compile time into the fold function. So this is kind of like what we saw earlier with monomorphization. You need to be ready for it. Now, we try to compile another iterator expression. This time, every integer is multiplied by 19 before the summation. This is done using the map iterator adapter. And again, on the surface level, everything seems to be dandy. There's a call to map and then a call to sum. Unfortunately, if you drill down into the functionality, you find out that specifically when this iterator expression is compiled in debug mode, the map function does not actually do anything, right? There's a call to a call to a call which does jack squat. Instead, the multiplication and the addition both live inside of the specialized closure which is spliced into the call to fold. So this should teach you something about how the Rust compiler operates. It has no respect for the autonomy or boundaries of any struct or function. If the compiler has decided that it's more optimal for the map function not to map and for the fold function instead to map in addition to folding, then that's just what's going to happen. So now we're mentally ready to look at the actual iterator that appears in the sample program. Believe it or not, the image on the left is equivalent to the for loop that you saw in the beginning of the talk. Now, this is about as complex as the creature on the right, called v3, which is an iterator which is built out of a call to iterate and then some iterator adapters like take, while, cycle, and take. Now, you're mentally ready to hear that when compiled in debug mode, most of those calls do not actually have functionality in them. Iterate doesn't do anything, take while doesn't do anything, cycle almost doesn't do anything. Cycle forces the compiler to allocate a deep copy of the initial state of the iterator, right? Because eventually the iterator is going to run out of items, and then we're going to have to need, in order to cycle, we need to access the first item in the iterator again. And without a copy of the fresh, pristine state of the iterator before it started being exhausted, there's no guarantee that the first item will be accessible. But other than that, cycle doesn't do anything. Finally, the call to take, as buried deep inside of it, the implementation of the function next for this hideous iterator creature that has been assembled here. And in this call to next, you're going to find all of the logic that you would have naively expected to live inside of the calls to iterate, take while, cycle, etc., etc. And the birthday iterator from the sample program behaves in pretty much an analogous fashion. For example, there's a function there called far enough in future, which in the assembly it lives 14 levels down the call stack from where the initial iterator is constructed. So hopefully now you know better what to expect when you are analyzing code that has been compiled from this kind of source code in debug mode, and it is my sincere wish to you that you never have to actually do that. So I hope that you have seen and heard enough today, so the next time you see a Rust binary being opened in your favorite disassembler, you do not recoil immediately in horror, but are able to recoil in a more calm and dignified manner. Thank you very much for listening.
Thank you so much, Ben. We have signal angels scouring the internet for people that are slowly oxidizing with questions. We're monitoring on Mastodon, we're monitoring on Matrix, and we're monitoring on IRC. This is Room Zeus, so use the appropriate hashtags. Our signal angels will take your questions and relay them to me. I see, however, in the hall we have already some questions, so please.
So you said that when you call a function on a trait, it just calls the function directly. How does that work with a boxed trait?
Actually, like I said in the beginning, I only had 30 minutes. You don't understand how much stuff went away before I gave this lecture, all right?
So
in
the
beginning,
answer is read the blog post.
Yeah, it's in the blog post. Yeah, the thing is, initially I had like 100 slides. It was a nightmare. I started talking, and I realized that like 2 hours had passed, and I was that's not good. So this is how we ended up with the talk as it is. There's a description of box actually in blog post, and Dean trait, and even a little taste of release builds actually.
Oh, nice.
So I welcome you to read up on it there.
Thanks, I'll read that.
Thank you.
I see that the crab people in the internet have a question.
So the internet wants to know, where did you get the graphics from?
The graphics, well, it's not like big surprise. I think everybody looking at those graphics would be able to guess where they came from. They came from like DALI. I have a paid ChatGPT subscription, so I asked it to generate images. Well, to be more precise, this was an ugly process. What happened was each time I needed an image, and I asked DALL-E to generate the image, it was, no, not like that. Please not like that. No, that's not what I asked for at all. Again and again and again, until eventually something like palatable was ejected out of this process. So like you were seeing just the shiny end product.
See, maybe there's a question on microphone 1.
Thanks for the introduction to what the Rust compiler does. So some people cannot choose to just close the binary again. They have to analyze it. Where would you say, like, which of these areas are most amenable to developing tooling to ease the process of reverse engineering it? And are you aware of any good tooling out there that helps with?
Actually, your question is the exact reason I had like this huge disclaimer slide in the beginning, because I knew that actually what I really wanted to do was just download some kind of Rust sample of a VirusTotal and reverse it. When I tried to do that, I spent the next half an hour in the corner weeping, and I realized that there's a first step that needs to be taken. I know that there are Rust tools for reverse engineering out there. There's the tech preview that X-Rays published, and there's, I believe, a name debungler also floating out there. But the state of the art, as far as I know, on this subject is really immature and lacking. And personally, when I'm thinking about what kind of next work I might do, this is exactly what I'm thinking of, taking all of this theory and turning it into actionable practice for people having to actually deal with these god-awful binaries.
Thanks.
I have to imagine that the internet has more questions about Rust binary analysis. No, how could that be? Thankfully, we have questions in the room.
Yeah, thank you for the great talk. So I was wondering, because all of the, or most of the basic blocks on the slides had this jump $+2, so we are jumping 2 bytes ahead. Is that something that the compiler just emits in the debug mode to, like, I don't know, tell you what is the basic block corresponds to in the code, or why is it there?
Look, I'm really sorry, but questions as to why the compiler does anything are a real crapshoot. I'm not sure I can answer that. I can give you like a counter example of my own. One of the things that didn't make it to this presentation was the way that the stack frames are built in these debug compiled Rust binaries. And the stack frames are much simpler. They only use RSP, no use of RBP, except in the main function, where some value is being strategically moved into RBP, and then all the arguments and all the variables are referred relatively to this invented value of RBP. I went to Reddit and asked on the Rust forum, like, does anyone know why this is the case? And no one had any idea. So I'm sorry, as I'm not sure I can answer this question.
Okay, thank you.
We can take another question from microphone 3. That's you.
Yeah.
This first.
You are microphone 2. Oh,
no,
sorry, you are microphone 3.
I am microphone.
That is my mistake. I'm so sorry.
What would the best way be to handle the enum values for some types? Is there tooling, or do you do it manually?
The work I did here was manually. Truth be told, really most of the challenge was getting over the shock of seeing the beta field being compared to 5, which was a value that shouldn't have existed. I mean, after that, it wasn't so difficult working manually. But of course, in the future, automatic tooling will have to be developed for this kind of thing. Right? I agree with you that it's not a good long-term plan for people to do this kind of thing manually.
Do we have a question for microphone number 5? Oh, sorry. Microphone number 2.
Is the allocation and interpretation of invalid values, like the 5th and 6th beetle, something scoped, or may it change along the same frame?
No, I believe that it's like the moment that the compiler decides how a sum type is going to be constructed, then this applies across the program. That is my impression, at least.
Thank you.
Microphone number 1 here in the front.
Thanks for your talk. It was only debug mode binaries that you showed, right?
Yes, that's right. There's some release mode binaries in the blog post, but like they didn't make it into this talk.
Is your experience that people deploy malware compiled in debug mode?
I'm sorry,
I presume you analyze malware by...
Yeah. Look, when it comes to Rust malware, like on our team, a lot of the experience has been just like the tweet in the first slide. It's like there's less analysis and more like despair. Now, regarding the question of how much debug binaries represent the real world, again, I made the disclaimer slide specifically to deflect this question. Right? There was a level of understanding that needed to be reached before we go into the real world and get like our face completely slapped there. So this was the intention of this talk.
All right, we have time for one more question from microphone number 5. I keep doing that. It's almost like I just wasn't paying any attention to your talk, and that's not a valid number. That's not the case at all. 1, 2, what? But where are you going? You had a question.
Microphone 2? Or 5? Okay, it's microphone 2, yeah. I also wanted to thank you for your talk, and I also wanted to ask a little bit about the release mode of the compiler. I think the compiler is supposed to strip away most of the abstractions, and how much does it work? So is there actually anything left of the complicated stuff you showed us?
Look, this is interesting. I think in order to understand optimized code, it's very important to first understand the unoptimized code the optimized code was generated from. And I think a great example of this is the for loop logic, because if you write a for loop like the one seen in the source there and you compile it in release mode, all of this complicated machinery of calling next and all of that is going to be stripped away. We're going to get a for loop just like from a C program. But if you write a for loop for a more complicated type of object, then these structures are going to appear again. Now, it's true that a lot of logic that you saw, a lot of this like useless lasagna logic, gets wiped away. Usually, because in release mode, because a lot of these abstractions are useless, they don't contribute anything in the trivial cases that you run across usually. So it's correct that if you take like a normal binary, a run-of-the-mill binary, which doesn't do anything too complicated, and debug it in release mode, you're going to get like a total wipeout, like an 80% wipeout of a lot of the stuff you saw here. But it's still important to understand what was wiped out and why.
So most of the
sorry, I have to cut you off. We're over time.
I'm sorry.
But thank you so much, Ben. Let's put our hands together.
Thank you.